All right, let's just jump right in because we're talking about maybe the single biggest mystery in all of science. It's this simple fact: 95% of our universe is, well, it's missing. It's completely invisible, totally unknown. We've got a map, a guide to help us navigate all this darkness. But here's the thing: that map, it's starting to fall apart. So take a look at this. This is basically the recipe for our entire universe. And this comes straight from the Planck satellite's final data. And honestly, the numbers are just mind-blowing. Almost 70% of everything is the stuff we call dark energy. Then you've got another 27% that's dark matter, and that leaves, a tiny little sliver, less than 5% for literally everything else. And that is the absolute key here. I mean, think about it. Everything we've ever seen, everything we've ever studied, from the phone in your hand to the farthest galaxy we've ever managed to photograph, all of it is crammed into that tiny, tiny 4.9%. The rest, the vast, overwhelming majority of our cosmos, it's a total mystery. We have no idea what it is.
Now, to try and make sense of all this, we've put together this amazing framework. It's called the Standard Model of Cosmology. It really is our best map of the universe. But, and this is a big but, as we're about to see, this map is starting to lead us in circles to some really big contradictions. And the irony, the two biggest mysteries it's built on, dark matter and dark energy, are the very things that are now breaking it.
Okay, so let's tackle the first big piece of this puzzle. We're talking about the invisible stuff that acts like a cosmic glue, holding everything together. We're talking about dark matter. So the first huge clue came from an astronomer named Vera Rubin. She was looking at how galaxies spin, right? And what she found it didn't make any sense. Physics says that the stars on the outer edges of a galaxy should be moving way slower than the stars in the middle. But they weren't. In fact, they were spinning so fast that the galaxy should have just ripped itself apart, flinging stars everywhere. There was only one possible explanation. The whole galaxy must be sitting inside a giant, invisible halo of something with a ton of extra gravity holding it all together. Okay, but that's still kind of circumstantial, right? Well, the smoking gun, the most direct proof we have, comes from this. Just unbelievable cosmic car crash. It's called the bullet cluster. And what you're looking at is what happens when two entire clusters of galaxies slam into each other at millions of miles an hour. It's an event so extreme, it actually lets us see the invisible. And this is where it gets incredible. So astronomers used X-ray telescopes to find all the normal matter, which is mostly just super hot gas. And that gas, when the clusters collided, acted exactly like you'd expect. It got all sticky, smashed together, and slowed down, piling up right in the middle. But then they mapped out where all the gravity was by looking at how it bent the light from background galaxies. And guess what? The gravity? It wasn't in the middle with the gas. It had sailed right on through the collision, totally unfazed like a ghost. You've got the normal matter in one place and the gravity in another. This was the proof. Dark matter is real, physical stuff, and it just doesn't care about normal matter at all. So when you put all the evidence together, a picture starts to form. Dark matter is like the invisible scaffolding of the entire universe. It created this huge cosmic web first, and only then did normal matter, all the stuff we can see, get pulled into the densest parts by gravity, eventually lighting up to become the galaxies and stars we know today. So we're sure it's real, but that just leads to the next huge question. What is it? And that brings us to the next chapter in our story, the decades-long, multi-billion-dollar hunt for the actual dark matter particle. For decades, there was one suspect that everyone loved. It was a particle called the WIMP. That stands for Weakly Interacting Massive Particle. And the reason everyone was so excited about it was something they called the WIMP miracle. You see, particle physicists who are working on totally different problems had predicted a particle with these exact properties should exist. And when they did the math, when they calculated how many of these things should be left over from the Big Bang, the number was a perfect match for the amount of dark matter astronomers were seeing. It was too perfect. It felt like it had to be true. But after decades of building bigger and bigger detectors, searching deeper and deeper underground, the results are finally in. The most sensitive dark matter detector ever built, LUX-Siplin, has given its verdict. And that verdict is a deafening silence. Nothing. No WIMPs. And you can't overstate how big a deal this is. This isn't just a minor setback. The beautiful WIMP miracle, the theory that seemed so perfect, it's failed. And that has thrown particle physics into a genuine crisis, forcing everyone to go right back to square one.
So, with the hunt for dark matter hitting a brick wall, let's pivot to the even bigger and frankly weirder part of the puzzle. We're going to talk about the mysterious force that's pushing the entire universe apart.
Okay, picture this. It's 1998. Two different teams of astronomers are out there using these special exploding stars, Type 1a supernovae, as cosmic measuring sticks. Everyone knew the universe was expanding, and their job was to figure out by how much gravity was slowing that expansion down. It was supposed to be a simple measurement. Except, they found the complete opposite. The supernovae they were looking at were way, way fainter and therefore farther away than they should have been. The only way to explain it was that the expansion of the universe isn't slowing down at all. Sometime in the last few billion years, it started speeding up. It was a discovery that shocked everyone and won a Nobel Prize. Now, it is absolutely vital we don't mix these two things up. Dark matter and dark energy sound similar, but they are polar opposites. Think of it like this. Dark matter pulls. It's the cosmic glue holding galaxies together. Dark energy pushes. It's the cosmic engine driving everything apart. Dark matter is clumpy. It builds that cosmic web we talked about. Dark energy seems to be perfectly smooth, everywhere, all at once. One is gravity's friend, the other is its enemy. Okay, so this is where our story takes another wild turn, because the discovery of dark energy, the very thing that seemed to complete our picture of the cosmos, has now plunged us into two new, even bigger crises. So our best idea for what dark energy is that it's just the energy of empty space itself. Einstein actually had an idea like this he called the cosmological constant. Sounds simple enough, right? Well, here's the problem. When we take our best theory of physics, quantum mechanics, and try to calculate how much energy empty space should have, the number we get is wrong. And it's not just a little wrong. It's wrong by an amount that is, well, it's basically impossible to even get your head around. It's wrong by a factor of 1 followed by 120 zeros. That number is so huge, if you wrote it out, it wouldn't fit on this screen. This discrepancy has been called, and I'm not exaggerating, the worst theoretical prediction in the history of physics. It's a flashing red light telling us that we are missing something huge, something fundamental about how space, time, and energy actually work. And if that huge theoretical problem wasn't bad enough, we now have a real-world crisis to go with it. It's called the Hubble tension. Here's the deal. If we use our standard model and look at the leftover light from the Big Bang, to predict how fast the universe should be expanding today, we get one number, around 67. But if we go out and use telescopes to directly measure how fast the universe is expanding right now, we get a different number, around 73. And the critical thing here is the error bars on these two numbers don't overlap. They're statistically inconsistent. The universe is telling us two different things at once. So our model literally can't connect the dots from the beginning of the universe to today. It's broken. But we might finally have a clue about why. Brand new data from this huge survey called DESI is hinting at something revolutionary. It's suggesting that dark energy might not be constant. It might be changing, evolving over billions of years. And if that's true, if dark energy is not a constant, that completely breaks the standard model. It means our whole picture is wrong. So, if our whole map of the universe is cracked, and its biggest ingredient, dark energy, isn't what we thought it was, what on earth does that mean for the ultimate fate of everything? Where are we all headed? Well, the next 10 years are going to be all about answering that very question. We've got a new fleet of incredible observatories coming online. The Euclid telescope just launched, and the Roman Space Telescope is right behind it. And they have one primary job, to map out the history of cosmic expansion with insane precision and settle this debate once and for all. Is dark energy a constant, or is it changing? And the answer they find, well, it determines how it all ends. If it turns out dark energy is constant, we're heading for a big freeze, a future that's cold, dark, and empty. If it's something weirder, something that gets stronger over time, that could lead to a big rip, where even atoms get torn apart. And hey, if dark energy can change and maybe even weaken, that opens the door back up to a big crunch, with the universe collapsing back in on itself. Everything is on the table. So here we are at this incredible moment in science. Our beautiful standard model of cosmology, our best map of reality, is failing us on two fronts at the same time. The search for dark matter particles has hit a dead end, creating a crisis for particle physicists, and at the same time, the model's predictions for the whole universe are wrong, creating a crisis for cosmologists. And all of this leaves us with one final massive question. Are these cracks in our map just little details we need to fix? Are we just missing a couple of puzzle pieces? Or are we on the verge of a true revolution in science? A moment where we have to admit our map is fundamentally wrong, throw the whole thing out, and start drawing a brand new picture of space, time, and reality itself.